All right, Werner Heisenberg. Um, well, we've all heard of him. He doesn't look the same, does he? He doesn't have a goatee. Um, and his work was a little bit different. But what Heisenberg's uncertainty principle is in words is that you cannot with precision know the location and the velocity at the same time of a subatomic particle. You can know one or the other, but you can't know both. That's his actual principle. That's the math. And we are going to do a little math today. And I do usually get you on the test to reproduce this. But, another way of looking at it is this is sort of interpretations of Heisenberg's uncertainty principle. Excuse me, that the act of measuring one of the two properties affects the other property. Well, that's true. So when you're trying to measure the velocity of a subatomic particle, you end up moving it from its original position. So you don't know where its original position was. That's basically what it is. And then there's the idea of measurement affecting outcome. Now, when I worked in manufacturing, we stole Heisenberg's principle, and we realized that. And this is just like everybody sort of in business knows that you can improve things, productivity, whatever, if you measure. A great example might be you're trying to lose weight. Well, one of the best things you can do, if you do nothing else, just get on the scale every single day and you will lose weight. According to Heisenberg. No, that's a mutation of Heisenberg's theory. But it's true, right? And the reason is, of course, just the idea that, you get on the scale. If you know you're going to get on the scale tomorrow morning, are you really going to eat another cream puff? Or are you going to put it away? Because you're going to have to deal with the consequences in the morning when you write down. When you have to go, sorry, not when you write down, when you go stand on the scale. So that's a mutation of it. But the reason why it's true, by the way, why measuring something affects its outcome, and I love this example, and often it shows up on the test, is, imagine you want to find out the temperature of this cup of coffee with precision. Without precision, you can do it very easily. But if you want to know precisely, like to the 10 millionth of a degree, what's the temperature? Well, as soon as you place the thermometer in that cup of coffee, the thermometer has its own temperature. So the thermometer, if it's cool, say the thermometer was actually quite cool and you put it in the coffee, maybe not by much, but we're talking about very small bits. The thermometer being placed in the cup of coffee will affect the coffee's temperature. Therefore, the act of measuring the temperature of the coffee affects the result. And that's the maybe easier to understand than we're going to get into with Heisenberg, but that's it. Same idea then with if you're trying to look at a subatomic particle, well, in order to see it, there has to be a photon of light shining on it. Well, the photon, not a photon, many billions, but when a photon finds the particle that you want to find, I guess that's an electron in this particular case. So I want to look down and find this electron. Well, the light that I send to find it hits it and alters its momentum. And again, so for Heisenberg's uncertainty principle to be real, I mean, if it's something as small as an electron, which is practically massless itself, a photon of light can affect its motion. With something as big as you or me, some light shining on us isn't going to affect our motion, at least any macro way. Anyway, so that's the basic idea. It does have an equation. This is not the equation we'll use, but this is actually looking at the uncertainty. So in momentum. So remember, P is momentum. So this is how far off your measurements can be. Uncertainty in position, it's just around the idea, it depends on what frequency of light you're using to find it. So if you use like a purple light that has a very low frequency, then you can find it with more precision because you can sort of pinpoint between waves where it is, right? But this red light has a much bigger wave, so there's more uncertainty in its position. So here's the equation. This is what we're getting into. And we're talking about uncertainties. And so delta means uncertainty, okay? So this leads to our equation, which is the product of the uncertainty in momentum and the uncertainty in position, x's position in this case, has to be greater than Planck's constant divided by 2 pi. Okay, this is the equation that Werner Heisenberg came up with. Now it can be simplified a little bit because momentum is mass times v. Mass is not really considered here. And you may have heard the joke, you know, a police officer pulls over two physicists and he says to the driver, he says, "Do you know how fast you were going?" And the physicist says, "No, but I do know exactly where I was," because he can only know one or the other. And this is the velocity and displacement, okay? So this is usually the form we're going to use. And this is the form that you're going to put on your formula sheet. This is the form we're going to practice with, okay? So again, what this means is the uncertainty in velocity multiplied by the uncertainty in position has to be bigger than h over 2 pi m. And the idea is that if the uncertainty is v is very, very precise, then the uncertainty in x must be big in order for this to be true. And that's why, you know, you can find one but not the other mathematically. Okay, so let's do this great example, and yeah, you will have to do this, so pay close attention. So we want to find the uncertainty product for a 1 kilogram mass, and the uncertainty product, as I said here, is just these two multiplied together. And then use that to find the uncertainty in speed or velocity for that mass if I want to pinpoint a 1 kilogram mass's position within 1 millimeter. Okay, so that just means that I want to be able to say that it's plus or minus 1 millimeter from 0.1 millimeter, sorry, from a certain location. So first of all, I'm looking for just this, right? That's the uncertainty product. So Planck's constant, 2 pi, 1. The only thing in there is the 1. It has to be kilograms. Planck's constant is just a constant, 6.6 times 10 to the negative 34. And so there it is. There's my uncertainty in uncertainty product, sorry. But now I want to find the uncertainty in speed. How far off will I be in a speed measurement if I want to be that precise with the location on a 1 kilogram, which is a pretty big mass in terms of quantum physics. So I know mass. I know my delta x is going to be I times 10 to the negative 3 to get from meters to millimeter, or millimeters to meters, right? Now I'm looking for this. So my uncertainty in v, you just keep your uncertainty right there. I don't know if you ever studied that in math, I can't remember. But you treat it just like an equation, except for you just leave it as this must be greater than. And sub in, sub in, sub in. Well, no worries. For a 1 kilogram mass, if I want to pinpoint it within 0.1 millimeters plus or minus in its location, then my velocity will have to have 1 times 10 to the negative 30. That's as accurate as I can be. But since we'll never be that accurate anyway, it doesn't matter. So for a 1 kilogram mass, Heisenberg's uncertainty means nothing. Okay? It's insignificant. However, same question, we want to find the uncertainty in speed for an electron. If we want to be able to pinpoint its location to within an atom. So an atom, say, has a diameter of 1 times 10 to the negative 10 meters. So I'm going to say, I just want to know within an atom. It doesn't have to know exactly which orbital, nothing like that, just within that atom. But how far off, that's my accuracy in position, how accurate can I be in that electron's speed? Okay? Look at this. Same equation, sub in the numbers, da da da. I'm off, I have to be off by at least 1 million meters per second. So if I want to pinpoint an electron's location within an atom and I want to find its speed, I'm going to be off by at least 1 million meters per second. Or I could be off by at least 1 million meters per second. So uncertainty is significant for quantum, smaller than the atom scale. So this is a calculation you should be able to do, okay? Is apply this formula right here. Oh, this is awesome. This guy is awesome. He's a professor at MIT, physics professor, probably going to retire soon, if not already. And just so lively and fun and love of physics. And anyways, here's his full video.
Heisenberg's principle indeed is very, very non-intuitive. Frankly speaking, I'd call it bizarre. But you can see it at work. Suppose I have a laser beam here. And I use laser beam because that's bright, but I could use any other light for that matter. And I make here an opening, a slit, a vertical slit. And here goes the laser beam right through the slit. Light goes on, and here I project this onto this wall, screen, projection screen. And what do I see? Well, you see exactly what you predict. You see here this laser spot from this beam. But now I'm going to make this vertical slit narrower and narrower and narrower. What now are you going to see? Well, you're going to see exactly what you predict. You're going to cut off the edges of the circle, and the spot gets narrower and narrower and narrower. But now you come to the point that this narrow slit, say, is only 1/100 of an inch wide. And now Heisenberg's principle comes in. Because now you know so precisely in the horizontal direction where the light is, that as it emerges from this slit, the direction of the light is no longer determined according to Heisenberg's principle. And so now what you're going to see, it's going to spread out in the horizontal plane, and therefore what you're going to see on this projection screen is going to get wider. Extremely non-intuitive. Because what am I doing? I'm making the slit narrower and narrower and narrower and narrower. And what do you see ultimately? That the beam horizontally becomes wider and wider and wider and wider and wider and wider and wider. Now that is very non-intuitive, but it's the way the world works.
It's the way the world works. Isn't he great? He's got an awesome book, by the way. He wrote a great book on teaching physics, and it's, which obviously more interesting for me, but it's pretty good. Oh, anyways, here's your next, oopsie, where'd it go? Your next thought experiment. I'll leave you to it. It's a good one. It's tough. It involves a little bit of thought on angular momentum, but I think it's intuitive. So you'll, unlike Heisenberg's uncertainty principle, which is very counterintuitive, non-intuitive, this is pretty intuitive. Anyway, I'll leave you to it.